Hello my friends, this is lecture 28, ray tracing with lenses and using thin lens equation. Main objective here is to learn how ray tracing goes with the lenses and how to use thin lens equation as the title suggests. We have two types of lenses, convergent lens and divergent lens. And as the name suggests, convergent lens converges the light and divergent lens diverges the light, just like the mirrors. But notice here, now we have transmission lights are coming from one side and passing to the other side, while versus reflecting in the mirrors. So that's what we will have here, coming from one side and divergent for the divergent lenses. They could be in different shapes, like shown here and there, overall. So that's what they are. We will do ray tracing very similar to the mirrors, and we will see that convergent lens again will be converging the light at a point, what we will call focal point, and divergent lens will be diverging the rays, but their extensions will meet a point which we will call focal point. We will have two sides of the lenses, so we'll show two focal points in either side, and on the side where the rays are coming from we will call near focal point, being near to the source of light, and the other side we will call far focal point. Spatial rays are also similar. Parallel rays refracts, passes to the other side, converging on focal point, and those coming from the focal point refracts as parallel to the axis, optical axis. Remember, we draw lines in the center. This ray would be going along the optical axis here, and so on. So the rays coming from the focal point refracts parallel, and those going to the center of the lens will directly pass. And we will do similar analysis. Our book says send 3 rays, but 2 are enough. It could be parallel ray, passes through the focal point. That one passing through the focal point transmits to the other side, passes as parallel. Where they intersect, we'll be having an image. And if the rays themselves will be intersecting, we will have a real image. Real images will be generally upside down. And then we'll look at the distance, and we'll complete the image of the object logically after that. So send in 2 rays from the tip of the object will take care of the situation. The third spatial one we could also send, passes through the center of the lens, and nothing happens there, just passes to the other side. That will be a ray coming along the normal actually. Most often we'll have real images on the convergent lenses, but if our object is closer than its focal point, this is the object here, closer than its focal point, the rays will have no way of intersecting on the other side. We will have then virtual images. We'll trace their extensions and we'll have virtual images, but what we will do will be the same. Send 2 rays, parallel, refracts, passes from the focal point. The one coming from the focal point refracts parallel, and look at their extension. Themselves will not be again meeting at any point. So we'll have a virtual image right side up, larger than the object, and we'll have that behind the object. Notice here the object and images are on the either side for real images. The object on the left side and images on the right side, but for a virtual image, object and image are on the same side. Both are on the left side, or it could be both are on the right side. I want to go back to magnification here that I mentioned briefly in the previous lectures. We want to use it a little bit more in here. It's the image distance over the object's distance, S prime over S over here, shown the image distance is S prime, object distance is S, and that's what we use, and a negative sign in front of it. One important thing we want to know is S prime will be negative if I have a virtual image for a virtual image. So since I have negativity in front of magnification, magnification will end up being positive. And S prime will be positive if I have a real image. If, oh, for, let's say again, for real image. So those are virtual images. And this tactic box summarizes what we said. Always go back to this tactic box and remember what we have to do. Spatial rays, parallel passes from the focal point on the other side. Focal point passes as parallel to the other side, and those coming to the center passes directly to the other side without changing direction. This question here is talking about a flower being here and asking what where its image would be. Two rays are sent for us, parallel passes from the focal point on the other side, and those coming along the focal point passes parallel. We look at their extension, we have this virtual image. Then question continues and asks us if the image distance is 12 centimeters, that's S prime. We would take that as negative because it's a virtual image. What would be the magnification? The object's distance is also given as 4 centimeters. Put in these values here, we'll have a magnification of 3. That means image is 3 times larger. If the object's height is h, image height would be 3 times h. I want to remind you here again, I briefly mentioned S prime over S is equal to H prime over H. So if the object is 3 times, image is 3 times farther away from the object, its height will be 3 times larger, directly proportional. This is a very nice question here. I'm gonna go through. We have an object, its image there, inverse equal to the object. As far as I can see here, it could be smaller, but regardless, this tells me I have a convergent lens here because real image is never formed by a divergent lens. Then question tells me, what if I cover the half of this lens? Will I still have the image? And for that, what I want to do is try to see if lights are able to pass, image will be able to form. So I'm going to try passing some light rays here. I can pass a light ray going through the center of my lens still. I can pass one going through the focal point. Assume this is the focal point. And it will refract as parallel, so I can still have an image here. But if there was no coverage, there will be many more of those rays passing from the top side as well. Now they can't pass. The image will be dimmer, but still I will have my image there, which is the answer. This is a summary of how image changes, and it's very similar to convergent mirrors. Only if I have my objects here, images on the other side for real images. It was on the same side for real images for the mirrors, if you remember. But if I start at infinity, my image will be at the focal point on the other side. As I walk closer to the lens, my image will be going farther away and getting larger until I reach the 2f point. At 2f will be equal, my image and my distance to the lens will be equal, 2f and our sizes will be equal. If I keep going closer, my image will keep going farther and getting larger until I reach focal point. At focal point I lost my image because the rays will be parallel to each other, and we assume it's the image at infinity. If I go any further than focal point, capital F here again is the focal point, my image starts being a virtual right side up, larger than me and behind me. Now notice the virtual image is on the same side as the object for the lenses, while it was the opposite for convergent mirror. It was virtual image is behind the mirror. Other than that, the change in type is same. Sizes are same. Real and virtual is the same. Divergent lenses also has 3 special rays, those that whose extensions are passing through the focal point. On the other side will refract as parallel. Let me show that. So this guy's coming. So all the other ones as well here, refract in parallel if its extension is passing through the focal point. If I'm sending one that is parallel, it will refract to the other side in a way that its extension will be passing from the focal point, second spatial ray. And the third one is the same as the convergent lens. Coming through the center will pass right directly without changing direction. And we use those to find the images. This page summarizes what happens. How do we find images? Send two rays, and where they intersect or their extension intersects, we'll have image. It turns out for convex lens, similar to not convex lens, sorry, the divergent lens, similar to divergent mirror, that we always have image smaller than the object in between focal point and the lens, and right side up virtual. It will be on the same side as the object for the lens case, while it was on the other side for the mirror case. If I'm only at infinity, my image will be at focal point. Other than that, always between focal point and the lens. Always virtual, right side up. So S prime will be negative, remember, negative. And when I put that in the magnification, minus S prime over S, I'm going to have a positive value for the magnification. For magnification, we can also look at the absolute value. It tells us how much larger or smaller the image from the object. So H prime over H or S prime over S can be used to find the magnification. This is a quick check question. Light rays are convergent to a point 1. The lens is inserted into the rays with its focal point at point 1. Which figure shows the rays leaving the lens? So if I'm inserting this, whose focal point is here, that means rays are coming to it, extensions passing through the focal point, and they will refract as parallel. Alright, this question here, a divergent lens at focal point 50 centimeters is placed 100 centimeters from a flower. Let's try to imitate that situation. I'm going to draw an optical axis and then try to draw a divergent lens. Always we imagine we send the rays to the center line here, so we don't worry about the thickness of the divergent lens. So we have focal point at 50. Let's approximate that. 50 centimeters. And we have a flower at about 100 centimeters. So somewhere here. It's very easy to guess what's going to happen here because there's only one situation. Image is always in between the focal point and the lens, in front of the object, in between the lens and the object, and smaller than the object. But let's send our rays, right? I'm going to send a ray parallel, and this ray will refract in a way that its extension is passing from the focal point. I didn't do a perfect job here, but it's looking alright so far. I can also send one whose extension is passing. Let me use a different color here. Whose extension is passing from the focal point on the other side, and that will be refracted as parallel. So I'm going to send that ray overall passing from the focal point, refract as parallel, and these refracted rays are never going to intersect, but their extensions will intersect somewhere here. I already knew that, right? It will be in front of, so I'll have a small image of the flower here. Here is my flower. Smaller than the object, right side up in between the focal point and the lens. Question further asks, if the distance of the image is 33 centimeters, that would be S prime, and would be negative 33 centimeters because we have a virtual image. What would be the magnification? Put it in the magnification equation, we'll find minus cancels, we'll have plus 0.33. There is a way to exactly find the distances without doing ray tracing, and that's the thin lens equation. Using ray tracing, we can send two rays and we find these two triangles here, and they are similar triangles. If we have similar triangles, similar sides ratios are equal to each other. So here this side H prime over that, so this pink triangle is similar to a green triangle, and we can use this side H prime over H is equal to this side of the small triangle over that, and that from similarities of triangles. Now we also know H prime over H is related to S prime over S is equal to actual S prime over S. So replacing here, carry this down there, I'll have S prime over S is equal to, notice this distance is S prime, this is S prime minus F, this is F, so I'll have this equation here. Working it out and sorting it out, we will have our thin lens equation. 1 over S plus 1 over S prime is equal to 1 over F. Although this is called thin lens equation, it also works for mirrors. So I can also use this to find the exact distances of objects, images, or focal points, depending on what value I know, for mirrors as well. There is an important thing to notice though. Some focal points are positive, some are negative, and there's a very simple definition for that. If I have a convergent lens or mirror, my focal point value will be taken as positive. If I have a divergent lens or mirror, my focal point will be taken as negative. And image distance could be positive or negative. If I have real image distance S prime is positive. If I have a virtual image distance S prime is negative. And the object distance is always positive. This figure here nicely summarizes it. Real image S prime positive. Mirror, this is a convergent mirror. Real image S prime positive, convergent lens. Virtual image, this is a divergent mirror, and virtual image for a convergent lens, if we have virtual image, S prime is negative. For a divergent lens, we also have always virtual image, negative distance. And here are the focal points: convergent, positive, divergent, negative. Convergent, positive, divergent, negative. And that's all. This picture here summarizes all images and how the distances vary. Maybe I'll add the magnification here to minus S prime over S. Convergent lenses, I have I'm starting at infinity, my image is at focal point, very small, come closer at 2f, my image is equal to me. As I come closer and closer, my image goes farther and farther and gets smaller. As I'm at focal point, my image goes to infinity, I can't see it anymore. Coming any closer, my image becomes virtual. Up to here I had real image, so distance is positive, and I have convergent lens, I have f. Focal point positive. At this point, my focal point is still positive, but my image distance I should take negative in Thin-Lens equation to get the correct answer. Everything is negative for divergent lens, image distance, and focal point. We always have virtual image, and we have a negative focal point. The same works for the mirrors. We have for convergent mirror, image works similarly. Notice again the real images are on the same side as opposed to on the other side for the lenses, and virtual images on the other side. But still for real images, focal point positive, image distance positive. Virtual images, focal point still positive, image distance is negative. And everything is negative for convex mirrors. Always go back to these 2 pages to review who is positive, who is negative. Here's a question. We have a convergent lens and we use it as a magnifying glass. Magnifying glasses actually we use are simply lenses. A stamp collector uses a magnifying lens that sits 2 centimeters above the stamp, and they give us a nice figure here. We have a stamp 2 centimeters above, an image actually forms behind. We want to have for magnifying glass, we want to have the object in between the focal point on the lens, so we'll see a virtual image on the other side, on the same side as the object. This is our object here, right? And this is our image larger than the object, so we will have some magnification. So what do I know here is S, right? Object's distance. So let's put it here, 2.0 centimeters. The magnification, which is equal to that, is 4. Now magnification 4, positive 4 tells me S prime should be negative, and I can solve for S prime knowing S and magnification as well. So alright, what is the focal length? That's what the question is asking me. So I say, if I know S and S prime, I can use a thin lens equation to find the focal point. 1 over S plus 1 over S prime is equal to 1 over F, right? But I don't know S prime. I have a way to find it though. I know magnification, I know S, I'm going to solve for S prime. And I'm going to find that S prime is equal to minus 4 times S. Notice this minus is coming from here, right? So 4 times S, and I see that the S prime is equal to minus 4. Multiply each side by minus 1 would get me there. And that's equal to minus 8 centimeters. Now I'm going to insert that here. 1 over F is equal to 1 over 2 minus 1 over 8, right? Or 1 over minus 8 is the same thing. That will give me, I multiply this by 4, I'm going to have here 4 up there minus 1 over 8. So 1 over F is equal to 3 over 8. Inverse in that would give me F, so 8 over 3. That should be about 2.67 centimeters. So that's thin lens equation. We also use magnification here and see how it works, and it could be useful. If I'm asked to find how much larger the image from the stamp, I go ahead and say that S prime over S is equal to H prime over H. S prime is 4 times larger, H prime will be also 4 times larger. That's a short way of solving the image height. This one is another one similar, a divergent mirror this time we have. So let's draw an optical axis and draw a divergent mirror. Something like that should do. Has a focal length of -2 meters. I'm going to put this down. We take the focal length of a divergent lens and divergent mirror to be negative. Question directly gives it to us as negative. So let's mark that point. Overall, let's assume this is -2. So the focal point. The focal point is actually here, but we also show it there. Use ray. Okay, wait, no. An object is 4 meters, so it's somewhere here. Let's use an arrow here for simplicity. Maybe I'll use red to make it a bit distinct from everything else. 4 meters, so about 2f away. This is 4 meters, this is 2 meters. I'm not going to show them as negative here. I'll just take them as negative in the equation distance, right? I can take them all as positive. Use ray tracing to determine the location of the image. I can always cheat, go back and check. The image location is always on the behind the mirror somewhere here, you know, virtual, smaller than the object. But let's do ray tracing. Send a parallel ray, right? It will reflect in a way that its extension is passing from the focal point. I can send one to the tip and send the reflected with the angle. That would be a good way to go here. I don't have a space for a lot of mistakes because it will work even if I might not be really precise here. Something like that. I'm looking at the extension of that guy. Somewhere here I'll see my image. And as I know, it should be so. Right side up, behind the mirror, virtual, and so on. That would be my S prime, right? That would be my S prime. And H prime would be the height of that object. So I found it. It's virtual, upright, between the mirror and focal point. What else? Behind the mirror. Also we can say, instead of between mirror and focal point. Alright, so we did that. It's virtual. We answer this now. And use the lens equation to find the exact distance. Alright, let's do that. We know S, and S is always positive, 4 meters. We know F, so we can find S prime, right? 1 over F is equal to 1 over S plus 1 over S prime. I'm going to take this whole guy to the other side as negative. It's positive there, so I'll say 1 over S prime is equal to 1 over F minus 1 over S. I'll put in the number, solve an inverse just to find my S prime. F is minus, so I should take it as minus here. They're all in meters. I'm dropping meters here. Minus 1 over 4. So I'm finding this, folks, is minus 1 over 2 minus 1 over 4. Multiply this by 2. I'm going to have 1 over S prime is equal to minus 2 minus 1 over 4. Minus 3 over 4. Minus and minus is now added, right? And finding minus value. S prime is inverse of that. So S prime is equal to minus 4 over 3. That's about 1.33 meters. and as it should be smaller than the focal point. That's it for this lecture. See you in the next one.